Hey everyone, this is question 92 from chapter 6. This problem is about a student swinging on a rope swing, and he lets go at the top when the velocity equals 0, okay? So the first part of this question asks us to find the angle theta here when he releases the rope. So to do that, we can do conservation of energy between E1, or 1, which is going to be the bottom of the swing, and 2, which would be the top of the swing, okay? And this is just a diagram I've drawn out to help us visualize this. So L is going to be the full length of the rope, and L minus H is going to be the difference in height that he swings. So when we do conservation of energy, E1 equals E2. At the bottom here, we're going to set his starting point to be the 0 height, so we're not going to have any potential energy. At the bottom, it's just going to be 1/2 mv1 squared equals, and then at the top, if he releases when his velocity is 0, there's no kinetic at the top, so it's just going to be mg y2, which we're going to call h, mgh, all right? So then h equals v1 squared over 2g. Okay, so that's our expression for h. But then how do we get the angle here? Okay, so if we look at this as a triangle, we can do cosine of adjacent, LH, over L, because we're trying to find H. We're trying to find the angle. Okay, so we're going to do cosine theta equals L minus H over L. Cosine theta equals, we could take out the L. So we can do 1 minus H over L. And then we have a expression here for H, so we can plug that into this. So cosine theta equals 1 minus V1 squared over 2GL. All right, and then from there we can solve. So I'm going to go onto a different page so this doesn't get too messy. So theta equals cosine inverse 1 minus, this is how we're solving for theta, 1 minus v1 squared over 2gl. Plug our numbers in, equals cosine minus v1, 1 minus 6 meters per second squared over 2 times gravity, 9.8 seconds squared, times L, which we're given is 10 meters. All right, and then that is going to give us a theta equal to, when you plug all that into your calculator, 35.28 degrees. And with sig figs, that's going to be 35 degrees. Okay, so now part B of this question asks us to find the tension in the rope when he releases, okay? So at the release point, the speed is 0, so there's no radial acceleration, okay? Because radial acceleration equals v2 or v squared over r. Okay, so if we don't have a v, then we don't have any radial acceleration. Okay, so then that means that the centripetal force, if there's no acceleration, there can't be any force. So the centripetal force must be 0. So we can write a free body diagram and solve for force of tension. All right, so this is going to be the kid, and we have F of t theta, and we have mg. And this, just as a reminder, will also be theta. Okay, so let's set up sum of forces. Let's do sum of forces so that t, so this is going to be our coordinate system, x and y, right? So sum of forces in the technically x direction, or we can call it the radial direction since it's the radius, but we'll say, or sum of forces in the y direction, excuse me, equals, or it's not going to be equals to, F of t, tension, minus, we have gravity, but it's only the parallel component of gravity, so it's going to be cosine, minus mg cosine theta equals 0, because we just said that there's no centripetal force. Centripetal force is 0 because there's no centripetal acceleration. Okay, so then we have f of t equals mg cos theta. And we can plug in our numbers. So ft equals 56 kilograms. Gravity, 9.8 meters per second squared, times cosine, the angle that we just saw for, 35.28. Plug all that in your calculator. F of t equals 448 newtons, which with sig figs we can round to 450 newtons. All right, so that is the tension of the rope at the top of the swing. So then part C asks us to find where the tension in the rope is greatest and what that tension is. So what's going to be the greatest tension in the rope during the swing? Okay, so we can do that. Again, we're just going to do Newton's second law. We're going to do sum of forces again, like we just did, but this time we're not going to plug in a specific angle because we're trying to figure out what angle and where that greatest force is going to be. So F of t minus mg cos theta. And this time, our acceleration, our force isn't going to be, it's not going to be equal to 0 this time because we're going to have some radial acceleration. So this would normally be Newton's second law, F equals ma, but radial acceleration is v squared over r. So we can replace that a term, okay? All right, so we're solving for force of tension, so just add this term over to the other side. So F of t equals mg cosine theta plus mv squared over r. Okay, so looking at this equation, we can see that f of t is going to increase as v increases because it's in the numerator and it's squared. And then cosine of an angle decreases as the angle increases. Okay, so then that means as this angle decreases, cosine is going to increase. So f of t is going to increase when theta decreases, and it's going to increase when v increases. So where are these two terms? Where do both of those hold true? Well, we said at the bottom of the swing, there's no potential energy and it's all kinetic. And then we also, at that point, the theta would be 0. So the greatest tension is going to be at the bottom of the swing. So f of t equals mg cosine 0, which we know just to be 1. But, okay, plus m v 1 squared over r. Okay, so we can plug our numbers in. Ft equals 56 kilograms. times gravity, 9.8 meters per second squared. Cosine, we already said is 1, plus 56 kilograms, 6 meters per second. And that is going to be squared over r, which we're given is 10 meters. Just the length of the rope. All right, plug that in, and you get 750 newtons. All right, so that's the greatest tension in the rope's going to happen at the bottom of the swing.